I congratulate whoever came up with the program. I think Patrick's talk and my talk are the most diametrically opposed and most distant. It maximized the content distance. I promise you there's not going to be a single equation on any of my slides. So I'm not doing any analysis. I wish I could, but I can't. I think I can say a couple of things about building systems and what you need to think about in that context. So I'm also not going to present any meaningful results, really. Maybe here or there, maybe there's a pointer to a tool or so that might be useful. I encourage you and invite you to go on a little speculation journey with me about how to do that. Well, that being said, I mean, you all know machine learning, you all know telco networks, right? I'm not going to waste time on that. So there we go. So the things I want to talk about is how do we know whether a machine learning approach is actually any good for telco networks, but maybe not only. And how do we avoid reinventing wheels? I think we as a community have a certain tendency of doing that. I'm not saying we are ignoring things that the IT community has come up with, but sometimes you feel like, okay, the IT guys have done that for 20 years, right? And we are playing catch up. And maybe that is something that we really shouldn't do. So maybe let me start with a couple tenets or statements, assumptions. Telco networks are large, they're widely distributed, so much so obvious. They are so large and so distributed that any central approach, any centralized approach to doing control, to do training, to do inference is futile. And that's already a point where some people start to object, but I think for the time being here, I would like to take that position that, yeah, it needs to be distributed. And also continuous training is probably necessary. It's unlikely that you're going to have the one wonderful model that will take everything into account and then can run for 20 years, right? And that's a point where you already start getting into fights depending on which industry you talk to. If you make that exact statement to a medical company, they look at you askance and think you're crazy. Of course, you do that once and have it certified and never touch it again for however long the system lives, right? Also, rail companies, logistics companies have very much that tendency. I think we can afford the luxury of thinking about, okay, retraining, adapting, things change, and we take that into account, et cetera, et cetera. Yeah, okay. Fine. And then, yeah, sure. Combinatorial optimization problems, resource management problems, et cetera, you know all of that, right? I'm not going to repeat that. So the fact is that you have to solve many problems. And because you have to solve many problems, many of these models are going to coexist inside such a network. And these coexistence can happen from different perspectives. It could happen because you have to solve different network internal problems, right? You have to do your, I don't know, handover process is an example I'll talk about in a few minutes. Your handover processes, your resource management, your antenna patterns for your MIMO systems. I don't know, right? There's tons of things you could do inside such a model and inside such a network. And you could do this very locally constrained, right? And you have one region where you do everything from one agent or closely guarded set of agents and another one, right? But what do you do at the border, right? So you probably have overlapping borders where agents start looking in each other's eyes and say, this is my domain, right? No, this is my domain. Here I take control. So you have agents conflicting with each other. You have conflicting activities there, even if it's just regional, geographic. The same thing could happen if you do hierarchies of agents or different time scales. If you have short time reactions from, I'm repeating myself, radio resource management. On the other hand, you do placement and scaling of functionality inside your network. That is something that takes place on seconds, maybe 2 dozens of seconds, very different time scales on which you do that. And, you know, once you start coupling control looms, funny things happen. And maybe even worse and maybe even more interesting, you have these things for very, very different types of jobs that you want to fulfill. You have things that are needed to operate your network, right? To make sure that the data goes from A to B in the most efficient fashion. On the other hand, you might have things that have nothing to do with the network, but use your network as a commodity infrastructure. It's the edge cloud argument. I think there's a talk tomorrow on edge clouds. I saw something in the program. So I'll be curious to understand whether this is going to be edge cloud for the purpose of the network or because you want to run your game server inside your edge cloud. No matter what, I think this is something that telcos, anytime I talk to telcos, they yeah, yes, maybe we should, but do we want to? So I think they're scared, right? They're probably scared of getting into this Amazon-style business model there, even though they could. The long and short of it, I think all of that means that it necessitates resource sharing for both inference and training inside your network, for different types of applications, for different types of models, or for which you know very different degrees of understanding how the model behaves, what resources it needs, etc., etc. And also they are very different in size. If I may digress like 3 minutes here a little bit and leave the telco domain, we are running one of the artificial intelligence service centers. There's 4 of them funded by the German government. And basically our job is to, well, spread the word about how wonderful AI is for all different types of industries, right? And this vast variety in what people need is showing up in that context as well. And we have people from very different industries popping up. You got your little craftsman who has heard about, hey, ChatGPT, do I need this now to do my bread rolls and to improve my bread baking process? Up to DAX companies, that was a cute example. DAX company talking about, yeah, that sounds interesting. We would love to have such an experimental environment at hand and try things out and see how different hardware works on our training problems. This is lovely. This is exactly what we want. Oh, by the way, we have 1 petabyte of data, which gave us a moment's pause. We have about 1.5 petabyte of storage available. So 1 petabyte for one of our customers would be challenging. And then the guy continued per day, at which we stopped that conversation, despite it being very interesting, but I can't deal with 1.5 petabytes per day. So there's a staggering range of size of tiny little problems that you can do on your laptop to, you know, the 1.5 petabytes per day type of example. Right. So what does that mean? How do we deal with that? So my consequence or my insight into that from the last 2 years or so is you need to embrace and accept the fact that everything is heterogeneous there. You have heterogeneous data sets and sizes, you have heterogeneous training problems, you have heterogeneous hardware, you have heterogeneous, everything differs. There's no one size fits all, there's not even one order of magnitude fits all. You have problems that need your entire cluster, you have problems that need 1/10 of a GPU. And I sort of sneaked in during Marco's talk. I sort of caught the second half of it. And I love the clustering and grouping together. I'll talk about the opposite thing a little bit, about chopping up things. And how do you do that? And what performance penalties you take and what can you do with that? So basically, where do you train what, with which resources? How do you infer with which resources on what? So it meets old friends from the placement and scaling problem family with the resource allocation family of problems. So everybody with me? Agreement, disagreement? Kind of makes sense? Okay, good enough. Good enough for the last talk of the day, right? So I think I'll skip that, you know that, right? This is just to illustrate, well, if you take a parameter server as a distributed work environment, weird things happen, funny things happen. If, for example, your network links become heterogeneous in latency, right? Your typical parameter server has in the back of its mind, I have this one master with a couple workers, typical master worker thing. This master parameter server gives out training jobs. You do an update on that, return the results, right? And in the very simplest case, this is all synchronized, right? So everything works on 10 milliseconds basis and returns results after 10 milliseconds, gets integrated, and next round happens. Lovely, wonderful. If you're inside a data center, this is great. Outside of your data center, when you run that in your RAN, in your, I don't know, somewhere in your network, yeah, sure, everything is going to work exactly like that. And you're going to have exactly the same latencies. No, you get sometimes long latencies, sometimes you get short latencies, sometimes you get slow workers or fast workers, you really don't know. So you need to deal with that. And similarly, your data isn't going to be homogeneously distributed either, right? Image classification example, you want to classify images into, what is it, 4 groups, 5 groups. And if everything is sampled nicely, equally and independently from the same distribution, sure, everything's easy, right? If it isn't, again, funny things happen. Of course, it converges down the road, but your conversion times are going to be terrible. The times you get decent accuracy is really bad. And now you need to think in either, do I want to think about in epochs, like the ML guys like to say that, okay, it takes me so many rounds. Yeah, fine. From a convergence argument, okay, but I don't care. I don't care about epochs. I want milliseconds. And the milliseconds and epoch thing is not the same in a heterogeneous environment, right? Because sometimes it takes longer, sometimes it takes shorter. So I don't care about milliseconds. I don't care about epochs. I want milliseconds. When you're back there, you start thinking about, okay, how do I compensate for heterogeneous data distribution? Do I just live with it and put more or less sampling at these different points? Do I start to redistributing data? I wish I had a good answer. I don't. Maybe something to think about. So there's a couple examples where we played around with that. Again, depends what variant of parameters you take, synchronous, asynchronous, you'll get different behavior of your accuracy over time or over epochs, depending how you measure that. Yeah, just as an illustration. Okay, so that's sort of the mental background for my playing field here. And then you start thinking, okay, this is interesting. Let's talk to some telco folks. In our case, T-Labs is around the corner. T-Labs, research branch of Deutsche Telekom. T-Labs is around the corner. Let's talk to them. Let's chat with them a little bit. And they basically said, this sounds lovely. Let's do a little student project. Okay, footnote, our bachelors have to do a 1-year student project together with an industrial partner. And that's exactly what we did there. And then I talked to them a little bit about, hey, what's a telco network and what's a mobile access network and so on. And they basically had a decent idea about machine learning. And then this happened. After 1 day of doing whiteboards and putting stickers onto whiteboards, they came up with tons of ideas of what all you could do, right? There are smart people there. So idea, right? All of them plausible, all of them you could do. And then, okay, let's narrow this down. Let's pick one and let's see how far we can get. And any favorite? Hard to say, right? So we went for one of them. Handover optimization in a cooperative multi-point process. You guys know that better than I do, right? So you got your mobile, you got your access points. I think I talked about this 2-3 years ago already. I think I mentioned that. I still like to bring it up as a nice visual example. It's easy to grasp, easy to understand. So you got your base station, you got your mobile, you got connected, you connect other mobiles, and you have other base stations. And then, well, you think about which do you connect where, because you don't just have your radio channel, you also need to share the resources at your base station and so on. And then you might want to do cooperative multipoint also to compensate for bad radio channels, right? The typical comp argument. Combinatorial explosion, typical optimization problem. You can write large and nice ILPs on that, and this is all good fun. Or you say that, no, this is all too slow, which it is. So let's train some agents for that, and you train centralized agents, and you do distributed agents. I'll skip over the details here, right? I talked about that. So central agents and so on. Nothing is going to surprise you. If you know comp and if you know reinforcement learning, this is sort of the straightforward approach you do there. The distributed version is a little trickier. That was the one that took us a little bit of thinking. Why? Well, you need to think about the greediness of each of your little distributed agents. And either you put the agent on the UEs, figuratively, right? You would do this as a mobile-assisted approach. You would still keep the control in your RAN, but you could imagine it being there. And then you want to grab as many resources, and then this quickly breaks down. So you need to do a little bit reward shaping for that to make sense. But basically, at the end, it's your standard adjusted Markov decision process there. So again, we ended up with a couple of variants of doing that, centralized inference or training, combinations of those. None of that is really key to my point here I'm trying to make here. I'm sure all of you have done, if you ever dabbled with machine learning in such a network, I'm sure you've done similar examples. And now comes my real question. What did you do next? Sure, you draw your Markov decision processes, right? Lovely. And let there be given states and let there be actions and so on and so forth. And if you're lucky, they are small enough to still be solvable in some meaningful manner. Probably they aren't, right? So you start building stuff, right? You develop prototypes and you dig through your typical libraries there. You could start digging through your arrays and whatever. And yeah, you can do that. You can do that and you get something out of that, and you can even publish that in decent venues. And then you do the next problem and you start from scratch. And you start from scratch. And then you start also thinking about, okay, array is fine, but this is a networking problem. I really want to have my network also nicely reflected in there. I also want to have the fact that I not just do central decisions. I also want to have the fact that, well, these decisions are based on observations that need to be transported to wherever my agent is. And maybe my agent is mobile if it's distributed. And my actions need time to be transported to where they are acted upon, where they actually take effect. So I need a network underneath, inside such a thing. And then you dig through your network simulators, and then you quickly find trained agents and so on. And then you quickly find, hey, look, this NS3 Omnet, NS3 is a natural candidate. There's NS3 AI, right? It does exactly what I just said. It does exactly that. Okay, let's do NS3 and AI together. Basically, it couples Ray into the NS3 event loop. Hey, lovely, right? Done. No, not at all. Cumbersome to use, difficult, hard, lots of code if you want to get it to working, and surprisingly buggy. Surprisingly buggy. For example, if you want to do multi-agent reinforcement learning in such an environment, which, you know, it's kind of the obvious thing to do, right? I have a large network, so you have multiple agents, and they have local observation spaces and local actions. Of course, I mean, it suggests itself, right? It just doesn't work. Basically, if you want to get technical for that, okay, sounds like an airport now. The way that the NS3 part and the Ray part exchange data happens via a shared memory system. So you're linking memory between these two processes. They both run at separate processes. And this shared memory system is not able, in the original form, is not able to separate between different agents. So anything you put in as observation into that ends up in the same agent, even if you have multiple of those running in Ray, which is, after you debugged it, obvious, but not before, right? So I showed you this picture, right? Okay. Sorry, stupid idea. I know I started that. I showed you this, right? That's what my eight bright bachelor students all want to do. They thought, oh, we can do at least half of that within a year, right? And then they started looking into, okay, it should be not too hard to do this with NS3. Not at all. Not at all. Buggy, etc. So basically what they ended up, and maybe this is something that might be useful for you guys, is actually an extension, bug fixing slash extension to this coupling of NS3 AI, the Ray library, getting this better together, in particular, doing a better job for supporting and enabling multi-agent reinforcement learning under realistic networking scenarios. So it gets structured into a couple of apps in the NS3 lingo. You got your agents, you got your observations, you can take separate action apps to work on that. And I think it ended up being an actually quite cute approach that is actually workable. I don't think the internal structure is so interesting here. Let's skip that. That's this shared memory, which we needed to restructure and rewrite to get this done. Also the event loop. It's really actually, I mean, if you sit back and think about what's really going on there, you take a C++ based discrete event simulator and you couple a Python based training system together, which is this is if you've ever seen a stupid system design decision, this is one, right? But you also don't want to redo the entire work, so you work your way around, and then you hold your discrete event loop at the right point. You wait for the events to come back from your array process. Then you need to scratch your head and think, okay, but that inference, let's say inference there would have taken so much, so I need to re-inject that back into my event loop in 5 milliseconds. Okay, I schedule events for that, but I also need to take care that this is actually serialized, because in a real system, I would only have a single environment to do that, and so on and so forth, right? So little nasty details that you need to do. Nonetheless, oh, wrong color scheme. So it boiled down to shorter code, nicer code, easier code. Shameless advertisement here, right? If you ever want to play with that, you're most welcome, and that's where you can find that. Defiance actually stood for something which I forgot. It was generated from some acronym generator, but sorry, I forgot what the acronym stands for. It doesn't matter. Right, lovely, right? So we're done. It's just simulation, right? Whoever believes simulators? Nobody, right? I really hope you don't believe a simulator. Incidentally, we played with the frequency reuse schemes in NS3, NS3 LTE, and NS3 5G. If you want to do ISIC, intercell interference coordination, boy, is that buggy. No, don't touch that. It's really, really bad. It's really broken. You don't want just simulation, right? You also want emulation. How do I emulate that? I mean, ideally, I want a real system, of course. Ideally, I want a real system and to run hundreds of thousands of nodes on hundreds of thousands of base stations, right? So I didn't even dare to ask the telco guys, the Deutsche Telekom guys, and maybe somebody here in the room has the ability to do that. That would be most interesting. But building a plausible test environment on real hardware is tough. So you emulate. What do you want to emulate? You want to emulate the actual running code. Fine, easy enough, right? We all know Mininet, so you can do distributed infrastructure. Yeah, running code inside Mininet is a bit tough. So you add the ability to run Docker containers to Mininet. Easy enough. ContainerNet, couple years ago. Fair enough, and that's good enough if you're happy to do all your training and inference just on CPUs. If you want to do that on GPUs, that still needs another couple more kicks. We got that kicked into submission to have actual GPU code, Wave in particular, again, to incorporate GPUs for that. And we also did fault injection, FaultyNet, maybe still needs a nicer name. So with this FaultyNet integrates ML. Okay. Sounds again plausible, right? ContainerNet as such is easily capable of doing tens of thousands of nodes emulated on reasonable hardware. With the actual GPUs, we didn't really try it beyond, I think, 4 GPUs because we didn't have any more. Should work nonetheless. And my goal here is to have something available down the road where people can easily replicate such setups on standard PCs, standard GPUs, and have edge computing environments, edge ML environments easily set up and tried out with realistic networking delays, with realistic bandwidth limitations. If anybody is interested in that, if anybody is interested in playing around with such a real emulation/simulation environment, I'd love to have test users. I'd love to have people playing with that and tell us everything that's wrong and everything that doesn't work. Right? I'm sure there's bugs. It would be a miracle. And we'll be happy to support and happy to help. Right. Yeah, distributed. Okay, lovely. So we're done. Yeah, you are done as long as you could dedicate GPUs to individual jobs, right? Then fine, check. what I said earlier, I think I want to repeat that. There are tons of situations and tons of jobs where modern GPUs are not fully utilized by individual training, let alone inference jobs. For realistic deployments, and I'm thinking now one GPU, couple GPUs per base station, per couple base stations, something like that. You need to think about how to share the resources of the GPUs. And that depends a lot on the concrete jobs you're going to run there. So you need to think about the operation environment, right? And let's just talk about one thing here, sharing of resources. In principle, various approaches, right? NVIDIA has caught up on that. Everybody else in that business has caught up on that. Yeah, you can share resources of GPUs. And basically, you can do time sharing in various fashions, or you could do space sharing. Basically, you can subdivide GPUs along the different coprocessors for simplicity, and have multiple jobs running on multiple subparts of the GPU. Takes time to reconfigure it. Interesting little scheduling problem there. If you have startup costs for your scheduling problem, and you can only do that when your machine is empty, right? So basically, you can reconfigure your GPU, make it better suited to the concrete job because its subdivisions better matches what your jobs need, but for that it needs to be empty. So I had a couple bells ringing when you said that you want to round up to 8, 16, 32, I think were your divisions. A couple bells were ringing here at that point. That might be a strong counter argument to saying that I'm actually not going to subdivide, or I subdivide it in fixed partitions. Right? I'd love to have a longer conversation on that. Or you just don't, and just do standard time sharing on that, as similar to what you would do with the CPU. And if you grab NVIDIA material on that material, well, there's a couple of standard approaches: streams, MPS, standard time slicing, MIG as this spatial subdivision. Okay, yeah, fine. Then you start scratching your head. What is nice and what is good for which job? And again, I wish I had more concrete answers for that. So far, we did synthetic tests with that. NVIDIA 800, sizable machine, sizable data rates for the memory, and you do your typical kernels out of your ML trainings, right? You do your single precision matrix multiplication, matrix addition with multiplication, vector additions, etc., etc. You numeric kernels, and you look at what's what. And you find that, well, some of them are nice. The details don't really matter, but up on the right, depending on the number of co-located workloads, think jobs, you see impact on the runtime or don't. And there's weird stuff happening, right? Just look at the two left group of bars, the left rectangle in the upper figure. That's weird, isn't it? So I'm co-locating additional jobs, and they basically see barely any interference between them. So the fact that there's a second job running doesn't impact the runtime of the other job. That's almost too good to be true, right? But it certainly stops being true as soon as things go up, right? Then I pay a price for co-locating things. I pay overheads, and the overheads are actually pretty high. So I see variance with that, and I see different behavior for different of my subdivision jobs. And I also need to think about memory. Memory footprint does matter, both the footprint as well as getting the data in and out of that. And again, it's getting late. I don't want to bog you into details here. If you look into details, there's one very natural candidate, and that's streams. Streams is basically in an operating system, you would call it a thread, right? They are threads, so it's all shared data set, no memory protection, etc., etc. So simplifying things, everybody can read everybody else's data. And that's the most efficient thing. Yeah, I mean, big surprise, of course. But when is this acceptable? When is it not acceptable from a very pragmatic operational scheduling job submission queue system? You need to think about what you want to do there. And again, I can only quote Marco. The IT folks have that. that exists. These notions exist that, okay, I can co-locate these jobs. I cannot co-locate these jobs because this is the same user. These are different users. It's okay to read the data or not. So are we reinventing the wheel? Do we want to build such scheduling systems for our telco networks again, such I'm distributing my my training jobs inside my network? And anytime I have this discussion, in the coffee break, we chatted over these 6G programs. This is one big fight, enthusiastic discussion point. Some people say, yes, absolutely. Telco networks are so different. We have our own requirements and we are so very special and so very different and everything is different. And I'm always asking for concrete examples. Give me an example. Show me exactly where what is happening inside a telco network really is different. Why can't we just take steal with pride, whatever Kubernetes / extensions actually do? And yeah, scale, I admit, and the multiple job submission queue entries and so on and so forth. I don't know. I don't have an answer. But again, this is something that begs for concrete evaluation in ideally a real system, but of course that doesn't exist. Maybe staging systems would be interesting. I don't know what your French 6G systems plan to do in this context, but staging environments where you can test that, test drive that, characterize, get profiles out of, okay, this job interferes with that job, not inference in the sense of taking conclusions, not interference in the sense of radio interference, but interferes from a performance perspective with that job in such a manner, can be co-located, must not be co-located because of data privacy, etc., etc. That would be gorgeous. That would be really useful. That would be really useful to know from a very practical, very real-life system-oriented, how do I operate such a network? And I think with that, I rest my case. And I'm happy to take questions.
Hi, thanks for the talk. Just want to follow up on the profiling question, because profiling is notoriously a moving target, because as your architecture changes, the same two jobs that coexisted perfectly well on one type of architecture will suddenly interfere in some weird ways in another architecture. So it's, it's not clear to me that we can actually get very far through profiling unless we do it for, every single, if you a big enough system, yep, you probably should take the time to profile things and provide guidelines, but your conclusions are likely to be somewhat wrong for the next system.
Yeah, I totally agree, and can give you examples for that. So we played with that on an H100, on an A30, and you do see differences. You do see differences there. Clearly, profiles are indexed by, okay, this applies to this type of machine. Absolutely. And again, that obviously begs the question, is it worth it? Or can I take the operational risk of just not caring and then fixing afterwards? Okay, I co-locate that and it just doesn't fulfill performance requirements, so I fix afterwards. Maybe, I don't know. But then that's again for telco operators to say that, okay, here I can take risks, this is fine. Maybe your handover process is 10 milliseconds late. No biggie. That is also missing. Sort of quality requirements for ML-driven decisions. If you look at standard algorithms and standard protocols, that exists, right? This, I don't know, 3GPP process chain, protocol, decision chain must be completed within 10 milliseconds in 95% of the cases, right? That exists, but for any of this ML stuff, it's all up in the air, right? And it's just not good enough there. Long, hot summer day. Okay, thanks.